Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I'd like to thank all of you for joining in on our webinar today. This is the last webinar of 2019. It's been an excellent year of webinars, and AFT and myself would personally like to thank all of you for being a part of them and for enjoying the educational content that we work really hard to provide for you all. And please be sure to stay tuned for the webinars coming up next year in 2020. We've got a lot of good ideas for new content. We have new features coming along with our next round of new versions for Fathom 11, Aero 8, and Impulse 8, and we're working on some new developments and capabilities. So be sure to keep an eye on our upcoming webinar page, aft.com, and then go down to webinars from the Learning Center menu, and then upcoming webinars. And we already have a few webinars for 2020 scheduled already. So be sure to register for those. And as usual, they're all free, and you'll be able to continue to enjoy the show. And so also with that being in regard, we would like to thank each and every, or we would like to wish each and every one of you a very happy holiday season, and hope that you all have a wonderful New Year's. All right, so what are we talking about today? Our webinar this morning is going to be discussing time and event transients. What are those? How do you define them? Really, this is a great webinar that goes back to basics, and the content actually applies to both AFT Fathom and AFT Impulse. So I'm going to be demonstrating both AFT Fathom and AFT Impulse today to highlight time and event transients and what they are. So if you go to the AFT products menu and then AFT Fathom to get to the Fathom page, scroll down to the bottom and you can find our add-on modules section here. And if you click on the extended time simulation module option, this is where you can find more information about the XTS module for AFT Fathom that I will be demonstrating today. So this module for AFT Fathom allows you to do transient flow modeling in AFT Fathom software, and it's a really useful and helpful capability. Also, for doing transient analysis, you can use AFT Impulse. So again, products menu and then AFT Impulse. And so AFT Impulse is going to model water hammer and surge in piping systems. And you might have the question, if you're able to model two different transients with two different products, which one do you use? Because both of them do transient flow modeling, XTS module with Fathom and AFT Impulse. So how are they different? Well, we did a webinar several months ago that illustrates very well the differences between when you would use the AFT Fathom XTS module for transient flow modeling versus when you would use AFT Impulse. And if you browse to our webinar library under the Learning Center, you would have to fill out the form, and then once you fill out the form, you can gain access. If you go to the AFT Fathom page for the Fathom pre-recorded webinars, it's this webinar right here. I'm going to circle it for you. It's called What Does Transient Analysis Mean? So in this particular webinar, I demonstrate an example of a piping system where I'm modeling a transient using the AFT Fathom XTS module. After that, I then take my AFT Fathom model and I import it into AFT Impulse, and then I do my water hammer and surge analysis on the same system. So if you watch that webinar, it's going to explain very clearly the differences between transient analysis in the context of AFT Fathom's XTS module versus the context of AFT Impulse. And it's a really good example. It'll give you some really good ideas on how you can use both tools in different ways. And that's outside the scope for today's webinar. So I'm going to be just talking about time and event transients in general. Now, when you come back to doing your flow modeling, 6 months from now, and you're wondering, what does a dual event cyclic transient mean again? Well, we actually have some video tutorials on that. If you go to our video tutorial page under the Learning Center, you can access all of our videos that are available on demand. And as you can see, I've already pre-filtered the list of videos. We have tons of videos, and right now I'm filtering my videos based upon AFT Impulse and technical videos. If you do that same type of filter, you're going to find these 4 critical video tutorials right here. It's called Time Transients, Single Event Transients, Dual Event Transients, and Dual Event Sequential Transients. And they are designed to be watched in that order. And so if you watch those 4 videos, it'll give you really good insight on how to use the different transient options once you get back into AFT Fathom XTS or AFT Impulse. And so even though these videos were developed with AFT Impulse, they also directly apply to AFT Fathom using the XTS module as well. All right, I'm going to go ahead and move the website to the side and jump into the software. So right now, I am currently showing you AFT Fathom. And when you're using AFT Fathom, how do you access the add-on modules? Well, there's numerous ways. One way is within the Tools menu right here. The other way is by using the button that is just to the left of the red status light. So if I was to click on that button right here, when you hover over it, it'll give you a tooltip. It's not showing up. Oh, there it is, modules. And so the module that I want to activate is the XTS module for extended time simulation. So if I check the box for that add-on module, I can then do transient flow modeling. So one of the changes you would see is when you drop a reservoir on the workspace and you open up the property window, you now have these 2 additional options for modeling either a finite open tank or a finite closed tank, and you can see how you can specify more input for the geometry. And the key thing is you will actually be able to track how your liquid level inside the tank changes during the transient simulation. That's mainly why you'd be using AFT Fathom XTS for transient flow modeling. So let's get to the guts of this though. What is a time versus event transient? If I was to drag and drop a valve onto the workspace and I opened up my valve, when you turn on the XTS module, or if you're using AFT Impulse, there's this Transient Tab. And when you go to that Transient Tab, there are 4 different options that can initiate your transient into the system. There's a time transient, single event transient, dual event cyclic transient, and dual event sequential. And so once you pick the specific transient that you want to work with, you would define a transient profile, and this transient profile in the data table is going to dictate how this device is going to behave in the system. Maybe you want to close the valve, maybe you want to open it. So that's where you can change the CV versus time in that particular scenario, and either of those will work fine. Now, you're going to see a lot of similarities when I open up AFT Impulse now. So if I open up AFT Impulse, you can barely change, or you can barely see the thing that changed. There are some slightly different icons and junctions here in the toolbox with AFT Impulse, but you can see here I am using AFT Impulse now. And if I was to go in and drag and drop a valve onto the workspace, just like I did in Fathom, here's my valve. I go to the Transient tab, bam, look at that. I've got the same 4 options that can initiate a transient for how my valve is going to behave during the water hammer event. So the time and event transients applies to both AFT Fathom XTS and Impulse. And now I'm going to go ahead and start off with demonstrating an example for you using AFT Impulse first. So let me go ahead and open up that model really fast. Give me one moment. Okay, so I just opened up my AFT Impulse model file. And if you were to browse to the analysis menu in AFT Impulse, you can see that there's two modes that you can work with for time simulation. There's steady only, or there's transient. So right now, when I have steady only, this is just like using AFT Fathom. So based upon the status light and the items in my checklist, this is exactly the same thing that you would be doing in AFT Fathom. You define your solution control, you set up your fluid information in the system properties window, you build the model of your piping system, and you define all the input for your pipes and junctions. So it's as simple as that. I have all three green check marks and a green status light. I can run my model and I can get results. And so if we take a quick look at the results here, we can determine where our pumps are operating, which are right around 2,300 gallons per minute. You can see the pump head that's required to deliver that flow. You can see what the velocities are and the flow rates in each of the pipes, etc., etc. This is normal, typical operation for this system when both pumps are operating on and I'm delivering flow to both process tanks here on the discharge end of the system. Now, here's where I'm going to start talking about the various differences between what we mean by time transients and event transients. I'm going to simulate a pump startup simulation for you. So my pump startup scenario is going to turn on the pumps, and I'm going to begin delivering flow through each of the flow paths. Now, here's the key thing is if you want to model a pump startup scenario to determine how long it takes your pumps to come up to speed and how long it takes your system to kind of balance itself out once your pumps turn on, your initial system condition needs to be in a state where there is no flow. That's really important to pay attention to. If you want to model a pump startup in your system, there has to be no flow in the system initially. Then you can start your pumps. It's kind of obvious. If you had your pumps already on, you wouldn't need to start them up because they're already running. They call me Captain Obvious. Anyway, how do you get the model into a state where everything is turned off and there's no system flow so that you can model your pump startup simulation? Well, the first thing that I'm going to do is I'm going to go to the analysis menu, and then under time simulation, I'm going to do my transient analysis. So now that I have turned on my transient analysis, you can see that there are two additional checklist items that have been defined. Now, section pipes and transient control is shown as already being completed because this was a model that I previously worked on, and I already defined that information, but let's pretend that those options were unchecked. So here's how we can mess that up. I can delete the pipe length and then re-add the pipe length. Let's make, well, anyway, when you need to complete these items, just click on the link here and this will walk you through the process. So here I can see what my pipe lengths are in the model. Longest pipe is 5,000 feet long, and the shortest pipe in the model is 20 feet. The controlling pipe is P6, which is also 20 feet. I'm not going to go into great detail about sectioning. That's another webinar that you can watch. So if you go back to our website under AFT Impulse this time, and you scroll down a little bit, there's a webinar right here called combine your pipes. This is a webinar where I talked about pipe sectioning and went into really good detail on that. So if you want to learn more information about that, watch that video, or I'm sorry, watch that webinar, or you can watch the AFT Impulse pipe sectioning video. Even though it was developed under Impulse 6, it still directly applies to Impulse 7. All right, so I'm just going to choose my basic sectioning here, one sectioning in the controlling pipe. Actually, yeah, that's fine. And then I'm going to go ahead and do my transient control. And the transient control is where you dictate how long you're going to run your transient analysis for. I think that my pumps are going to come up to speed relatively quickly, so I only want to capture what's going to happen in the first 10 seconds of my transient analysis. So in 10 seconds, my time step is 4 milliseconds, and I've got 2,300 time steps within that time frame. You can also dictate if you're going to model transient cavitation. You can model, or I'm going to save all the results for all my interior pipe stations. So when Impulse breaks up your piping into bits so that it can do the method of characteristics calculations, there are internal pipe computation stations where we're doing the calculations at. So I want to include every internal pipe computation station so that I could graph parameters in those interior stations if I want, and I can do my animations of my results a lot more effectively. So I'm just going through here and I'm setting everything up. I'm going to save my output results for my junctions and click OK, and there we have it. So now I've turned on transient mode. I have all of my checklist items completed. Now I have to get the model into a state where there is no flow in my system. Okay, so this is what we call a special condition. The special condition, let me go ahead and choose one of the valves here, is this valve right here. Once you select a valve, you'll see this red circle with the slash through it on the Workspace toolbar. That's our special condition tool. So if you select a junction and then you click this on and off, that's one way that you can toggle on and off the special condition. So in this particular case here, if I click on the special condition button, here's what happens. First, I'm going to see a little red X. That little red X indicates that you have a special condition defined for that particular object. In this case, the valve has a special condition of closed. If I was to open up the valve property window by double clicking on it, on the optional tab, this is where you can find the special condition on the optional tab of any junction window. So I've closed off that valve, and when you close off the valve, AFT Impulse also knows that there's no flow in this flow path right here. That's why it changed the pipes to dotted lines. So when I close the flow off with my valve, here's where the special condition is, and now the pipes know that there is no flow in that part of the system. So that's the first thing I need to do, is apply special conditions to my junctions, which will set the system into a state where there's no flow. So I'm going to go ahead and select this valve, and I'm going to set the optional tab to have a special condition of closed. Now I have no flow in my suction piping. However, you can see that these pipes in this part of the system are not dotted lines. That means that you could potentially have flow between these two tanks if there were elevation differences between them or pressure differences. So that's why these pipes have not been dotted yet, because you could still have flow in that system. So what I need to do is open up this valve here, and I can either go to the optional tab and click closed, or I can select the valve itself and click the red circle with the slash to it and set the special condition to be closed. Now I have all dotted pipes in my system, that means I have no flow in any of the pipes in the initial conditions for my scenario. So that's good. I don't have any flow. However, I need to do something to my pumps. So I have no flow in the system, but we need to do something to our pumps. If I open up the pump here, you can see that I have defined a pump curve. This is going to dictate how the pump performs in the simulation. And then if I go to the variable speed tab, you can see that we are operating the pump at exactly 100% speed. So if I was to just click cancel, I don't have any special conditions applied. So what this means is if I don't do anything to the pump in this particular state, the pump is going to deadhead against both of these two discharge valves, and that's obviously not going to simulate our pump startup scenario. So I have to turn the pumps off as well. How do you do that? Well, you could simply go in and select the pump junction and then click the circle with the slash through it to apply a special condition. However, there's a caveat to when it's useful to use that button and when you shouldn't. So when we looked at the valve junction, there was only one special condition that you could apply. It was either none or closed. So if I open this up, you can see that there's only one special condition to set that object to be closed. For some other types of junctions, there is more than one special condition. So let me open up the pump here, and I'm going to go to the optional tab. Here's where you can find the special condition for the pump. So as you can see, I actually have two different special conditions that I can apply to the pump. There's pump off with no flow, and there's pump off with flow through. In this particular case here, I am modeling a startup scenario for a centrifugal pump. So if we go back to the pump model tab, this is a centrifugal pump curve that I have defined in my system. So if you have a centrifugal pump and you turn it off and you unplug it from the outlet, the pump is going to be off. However, if this valve was actually open, you might potentially have flow through your system. So let me change this up a little bit. Let me take these two valves and I'm going to open them, and I'm going to take this pump right here and I'm going to use pump off with flow through. So if I use pump off with flow through, you can see how the lines have stayed solid. They're not dotted lines. So what this indicates is that the red X means I have a special condition applied to this particular pump, but I still have flow through that flow path in the system. In reality, if you unplug your pump and you have everything open downstream, you could have flow in that system. And if you have flow in the system, that flow could cause your pump impeller to change. And that's not something that's going to be modeled in Impulse. So this is where, when you are modeling a centrifugal pump, the correct option to use is pump off with flow through. The pump off with no flow option, this causes it to act like a positive displacement pump. If you're modeling a positive displacement pump and you turn it off and you unplug it from the outlet, it's going to function like a closed valve. So if you're modeling a positive displacement pump instead, then you need to use the option for pump off with no flow. That's the correct option for a positive displacement pump. For a centrifugal pump, which is what I was using before, let me just go ahead and cancel out of there. My centrifugal pump is going to use pump off with flow through. So this tells me that I have a special condition on my pump. And then because there's only one special condition for valves, I'm just going to go ahead and select that valve, click on the red circle with the slash to it, and bam, that closes off the flow through that path. I'm going to do the same thing with the other pump as well. So here's my other pump. and I'm going to go to the optional tab. I'm going to say pump off with flow through, click OK, and then I'm going to select my valve, and I'm going to hit the red circle with the slash through it. So now my entire system has no flow in it, and I am now simulating an initial state where there's no flow, the pumps are turned off. Now I want my system to come online. So if I wanted to, I actually could run this model. So because I'm running a 10-second simulation period, it'll take about 4 seconds. When I go to run this, we actually will be able to calculate results, and the results are going to show that we have no flow for all time steps. So if I look at my pump summary, everything's at 0 flow. If I look at the transient output data for my pipes, and I expand this, I have no flow, etc. So if I move the time slider, this is all basically 0 flow. Okay, so you can do your transients analysis and this won't do anything. So this is where you define your transients to allow the system to come online. So I've closed all 3 of my valves, and I've turned off my 2 pumps. So now I need to set transients for each of these objects so that my system can come online. So let's go ahead and do this one by one. I'm going to start by going to the first pump junction, and I've defined a pump curve. And when you want to turn your pump off, or I'm sorry, when you want to turn your pump on when it's initially off, you go to the Transient tab, and this is where you define a type of transient. Well, if you've never used AFT Impulse version 7 before, and you've only used Impulse 6 or previous, this window looks a little bit different, and we've completely redesigned how we do our transient modeling for pumps in AFT Impulse to try and make it a lot more intuitive. So that's why if you go to the transient window here, you're going to see pictures that will show you what you're trying to do or what you need to do instead of the drop-down menus like how we had in previous versions. So here's what I need to do. Because I have very limited data, I only have a pump curve. I don't have any information for efficiency or power. Also, if I was to close out of the pump window here, I don't have any information about my rated pump speed. So because the only information I have is head versus flow, this limits me on the type of pump transient that I can model. So because I'm missing a lot of data, I'm not able to use a pump transient with an inertial model. So those 2 items are grayed out. If you were to click on this little button that says, why are these disabled? It's going to tell you that you have some information missing. So if I want to turn my pumps on, the best that I can do is a speed versus time option. So I chose speed versus time, and once I check that option, you have the same 4 types of transient initiations like how I showed you before with the valves. Now, for this simple scenario here, I'm just going to start off with doing a very simple time transient. So if you choose a time transient, you have to set your very first data point to a time 0 value that reflects the initial condition of that object. So because the initial condition of this object is off with flow through, the first data point has to reflect that and be consistent with it. So if I was to try and say at time 0, my pump is operating at a 100% speed, here's what's going to happen. It's going to tell you that you have inconsistent input. Your steady state speed is 0% because of the special condition. However, the initial data point for the transient speed is 100. So this is a little safety net that's going to pop up and say, hey, you told the pump to be initially off, but the transient that you're trying to specify to turn your pump on, it does not match what you're telling it to be initially. So this is going to be a message that will warn you if things are not consistent with themselves. So now if I click OK and I change this to be 0% speed, there we go. That makes the message go away. However, obviously, if I go in and I specify a time transient and I say that at time 0, the percent speed is 0, and I don't have any other data down below, this pump is never going to come up to speed. It's going to stay at 0% through the entire 10-second transient simulation that I've defined in my transient control. So this is where we need to have another data point. I'm going to assume that my pump goes from 0 to 100% speed within 2 seconds. So because I don't have any other information for the pump efficiency or the rated speed, and I'm not able to use one of the more accurate and sophisticated inertial models for a pump startup, I'm just going to assume a very basic linear ramp up in pump speed, which maybe it does perform in this way, but maybe it doesn't. This is why it's helpful to have more information so that you can actually account for inertial effects for your pump transients. All right, now when you choose a time transient, I mentioned how this very first data point is really important. Not only does this first data point have to cause your value to be consistent with what you've defined in the initial state, this time 0 value is going to be the same time 0 value that you've defined in your transient control. So if I'm telling the pump to start at 0% speed at 0 seconds and then ramp up to 100% speed in 2 seconds, because I'm using a time type of transient, this transient profile will always happen no matter what. It will initiate and the pump will come up to speed exactly as how I've defined it in this transient data table here. And when I specify that time 0, that's the same time 0 as the start time in my simulation duration. Okay, so if I don't want the pump to do anything for 5 seconds and I want to use a transient model, I can have this be starting at time 0. And if I wanted that pump to just sit there for 5 seconds and do nothing, what I would do is I would go back to my transient table and I would say at 0% speed at 0 seconds, in 5 seconds, stay at 0. Don't do anything. And then the next 2 seconds would be at 7. That's when it's going to ramp up to 100% speed. So this is where you can specify a time delay with a time transient, is you build your time delay in to your data table. So when I do my transient like this, you can see how the pump speed is 0 second, or it's at 0% speed for the first 5 seconds, and then it ramps up. So again, this transient will activate no matter what. There's no criteria required. So however you specify this data table is how it's going to act with this time transient. Now, I'm not going to do a time delay. I'm going to just go from 0 to 100% speed in 2 seconds. Here's my transient profile, and there we go. And I'm going to do the same thing for the other pump. But since I already defined that data, I don't want to have to go through and click on all these buttons and enter all that information. There's an easier way. Since I already defined it once, I can click on this drop-down menu where it says copy data from Junction, and I'm going to click on pump J2. And the information that I'm going to copy over is the information that was on the Transient Data tab, which is this tab from the previous junction. So those are the boxes that I'm checking to transfer over. Let me erase the drawings. When I click OK, if I go to the Transient tab, look at that. All that information is there. I've defined my speed versus time without inertia. It's using a time-based transient, and the pump is going to come up to speed within 2 seconds. And click OK. Now, I have these two discharge valves, which are also going to need to open to allow flow through the pump. So when I start my transient simulation, these two pumps are going to come up to speed just like how I told them to. If I do not define a transient input to open up these valves accordingly, then that flow is not going to go anywhere, and I'm going to deadhead against my valves, and that's a very bad thing that you don't want to have happen. Now, when I define a transient, you see the little letter T here. That little letter T means that you have a transient defined for that particular object. So now I'm going to go into my valve, and for this particular valve, it's initially closed. The main operating condition is the CV is 1,000, but it's not operating there, it's closed. So if I go to my Transient tab, I'm going to do a similar type of transient, but instead of doing a time-based transient, I'm going to do a single event transient. And for single event, I'm going to click on an event type and call it time absolute. So here's the main difference between time transient versus any of these event transients, is when you specify an event transient, criteria has to be met before your transient data profile can proceed. Now, because I have chosen the option to use a time absolute, when you use time absolute for the event type, that actually causes your transient profile to mimic the start time of your transient control. So your time 0, it's going to match the time 0 in your transient control when you use time absolute. Now, if I want to do a time delay right here of 10, if I did 5 seconds, and then I want my valve to open, at time 0, it's at 0. So a closed valve for a CV has to have a CV value of 0. That represents a closed valve. And then maybe I want to go up to 800 and then 1,000. Okay, so if I set the time absolute value to be greater than 0, because I've specified 0 here, this 0 corresponds with time 0 in my transient control. So if I define time 0 right here, and then this profile, this is going to be the exact same thing as if I did just a basic time transient with the same data. Now, if I was to choose 5 seconds, what happens is it's going to let the clock run when I start the solver. It's going to start the clock, and this transient profile is not going to happen until after 5 seconds into the simulation. So if we look at the graph here, because I have specified this as my transient profile, this is how the valve is going to come open over time within 3 seconds. But this time 0 is not going to be at the beginning of the transient period because I've specified 5 seconds. So what this is doing is when I specify a time absolute of 5, that's my 5-second delay. So here I would have my first 5 seconds, and then my valve starts to open. But I'm going to set that to 0. So my valve is going to open immediately. So here's how my valve opens. I click OK, And I'm going to do the same thing for the other valve. I'm going to copy that data from J3, and we just do a quick check. Everything looks good, and click OK. So my two pumps, they used a time-based transient, where the start time of that object is at time 0 of the simulation period. Then my two discharge valves that are immediately downstream, instead of using a time-based transient, I used a single event, but I chose time absolute as the event, and I said 0. So this 0 corresponds with the time 0 in my transient control. So this will cause the valves to open at the very beginning of the transient simulation. Last but not least is my second valve, or my third valve right here, which leads to process tank number 2. So if I open up this valve here, it has a different fully open CV value of 500. The valve is initially closed, and so for this particular valve, maybe I wanted to go from 0 to 500 in, let's call it, not 235, I said 2.5 seconds. Now, I'm not going to use a time transient for this particular valve. There is logic where this particular valve, let me move it down here a little bit. This valve is actuated based upon the pressure right here at this location of the system. So the actuation criteria is such that when the pressure at this particular location gets to be greater than 45 psig, that's what's going to activate this valve to start opening. So that's what's going to use a event transient. So if I click on single event, there are a whole slew of different events that you can use. As you can see, there's a lot of them. And all you're doing is you're setting up the criteria that's going to cause this transient activity to happen for this component. So in this particular case, it's going to open based upon pressure. So I'm going to say based upon a stagnation pressure greater than or equal to 45 psig. And then you need to pick a location. So this is where you can do some various control type of modeling with very simple transients in AFT Impulse and AFT Fathom. So here, I had to specify where this is based upon. So it's going to happen based upon the pressure at the outlet of pipe P7. So when I set this up as my criteria, when the pressure at the outlet of P7 gets to be greater than 45 psig, that's going to cause this valve to start opening with that transient profile. So that's an event transient. And because there's a single event, I'm only doing one. So we'll click OK, and everything is all set up, and I'm going to go ahead and run my simulation. All right. So if we take a look here at our results, we can monitor what our maximum pressures and minimum pressures are and all that stuff. There's a whole bunch of red warnings here that after you go through and you look at them, you can learn that they're really not that severe. The important thing is when you see warning messages, be sure to actually read them so you know what they're saying. And then if you're still not sure what it means, click on it and pay attention to what this is telling you, where hit the F1 button on your keyboard. That way you can read our help file for that particular message and you'll get a better description of what it actually means. So let's look at our event messages by time. So here, this is going to tell me when the event messages take place. So let's break this down really quick here. Let me dock my output window to the bottom, and then on the workspace, I'm going to go back to my model here. And what this is telling me is here's when these three valves are changing state. So what this is telling me is that valve J3 and J6, these two valves right here begin opening at this time frame. Well, that's because I told them to open up at time 0. Well, this is 4 milliseconds, and 4 milliseconds is our time step. So what this is telling you is that these valves they're opening on the very first time step there. Now the third valve, J9, this guy, he doesn't start opening until 1.5 seconds. So what that tells me is if I was to look at the pressure at the outlet of this pipe, I should see that the pressure would equal 45 psig right at 1.5 seconds. Now the reason why it's telling me that these two valves are opening, but it doesn't say anything about the pumps, is because I used a time-based transient here, and I used an event-based transient here. So this is something worth noting is if you are looking at the transient window and you choose time, for anything that you choose time, they're not going to show up in the event messages tab in the output window. However, as long as you go in and you specify a event transient, which as you can see I've done right here, I'm doing an event transient and I'm saying it's at 0. When you do an event transient, those will appear as messages in the event messages tab that will tell you when those things are actuating. All right, so that looks all good. Let me go ahead and reset my panes. You can create graphs directly from the workspace. So if I want to take a look at how my pumps are coming up to speed, I can select both of those pumps, right click, and I can generate a transient graph for the pump speed. And there we go. There's not really anything that's exciting about this because this graph is just it's showing me that the pump is doing exactly what I told it to. So if it was doing something different, that wouldn't be good. But this is a good sanity check where the pump is starting up just as I expect. So that's good news. Let's take a look at the two discharge valves. If I select those two valves, then right click and look at the valve CV, they are doing exactly what I told them to, where at time 0, they are initially closed and then they begin opening right away. Because even though I used an event transient for these two valves, I said that on my event transient, use 0 as my criteria. So this will start happening from the very beginning of the simulation period because I chose 0. So this is another good sanity check to see what's going on. Last, let's take a look at the final valve that leads to process tank number 2. If I do a transient CV graph for that valve here, you can see how nothing happens for the first 1.5 seconds, and then you can see where the valve starts to open, and then it's fully open within 2.5 seconds there. Now, I'm generating these graphs from the workspace, but you can do the same thing on the graph control window here on the Transient Junction tab. So all I've done is when I've created those graphs, it just adds those transient junctions for me. So here you can see I've got my 2 pumps for the transient junction. I have 2 valves for transient junction, and then I have 1 valve. Now let's take a look at the pressure at this particular valve as well. Actually, this valve, it's actuating not based upon the pressure at the valve, it's activating based upon the pressure here. So I'm going to select this pipe and I'm going to show the pressure just for the outlet of that particular pipe. So if I select the pipe and I right click and say generate a transient pipe graph, let's look at stagnation pressure. Let's just look at the outlet of results only. Now, I'm showing my units right here in PSIA. The criteria was based upon PSIG. So I'm going to go in and I'm going to change my unit to PSIG and then just regenerate that graph. And then I'm going to right click on the y-axis and I'm going to put in tick marks every 5 PSI. So if I was to draw a line right here at 45 PSIG, I can then right click on the x-axis and let's do every quarter of a second. I can then draw a vertical line. Pretend that's vertical. This data point right here is right about 1.5 seconds. Well, how can you tell that even better? Click on this crosshair tool. Let me circle it for you. Here's the crosshair tool, and when you click on the crosshair, wherever you put your mouse, that's going to show you a data point on the graph. So here, when I go up and up and up, you can see how the pressure increases, and then right when it goes past 45 PSIG, bam, that's the same time that this discharge valve is opening up. So what I'm going to do now is I'm going to create a graph folder. New graphs. I'm going to file this away. I'm going to call it pressure at P7 outlet. And I'm going to show my pump speed versus time. So I'll call this pump speed. And then last but not least, what I'm going to do is I'm going to select pipes in a flow path. And after I select the flow path on the workspace, I go back to my graph results. I'm going to click on the green plus sign to create a new graph tab. Click on profile, click on workspace. I'm going to do an animation for pressure. And I'm also going to put the flow rate on there as well. All right, so I'll call this P and V animation. And don't worry, there's a method to my madness. All right, so what I'm going to do is I'm going to move this graph up. So I'm looking at my animation, the pressure at P7 outlet, and the pump speed. And what I'm going to do is I'm going to right click on the folder and I'm going to load all those items into the same tab. And so now, when I go to run my animation, we're going to look at several things at the same time. We're going to look at pressure at the whole entire flow path. We're going to look at the flow through the whole path, the pressure at P7's outlet, and the pump speed. So this is a really effective way to be able to analyze your results. You could click on the record button, and that'll record your animation as a MP4 file. I'm just going to click on play. So now the pumps are coming up to speed. You can see how pressure is building up in the system, and we are starting to get flow upstream of the system. But here's J8. Here's branches. Here's J9. So this valve is initially closed. So it's going to take a little while until we start seeing flow down in this section of the system. So we'll just let that keep building up over time. So you can see how we're starting to get some tiny flows into the system. Right now, our pumps are just about to hit 40% speed. You can see how the pressure is continuing to build up at the outlet of pipe 7, which is right at that branch. And then right about now is when we start to finally have flow. It's that downstream system. Bam, that's right when that discharge valve J9 opens. And now this is how we can see how the pressure and flow builds up in the system. And you can play it a little bit longer and you can see how those pressure and flow oscillations pass back and forth with each other for a little bit once those pumps have come up to full speed. So that's my pump startup simulation, and I demonstrated how to do a time transient with the pumps, a event transient using time absolute, and then another event transient which causes this valve to open up based upon a pressure somewhere else. Now, let me go ahead and open up Fathom, and I'll illustrate another type of event transient modeling. So let me go ahead and open up my model here really quick. Give me just a moment. All right. So here we have a system that is doing transient, where I'm running the simulation. After you turn on XTS, you have steady only or transient options as well. My transient control, I'm running the simulation here for 3 minutes, and I'm doing data for every 5 seconds. Keep in mind that Fathom is not going to be accounting for any water hammer that could be happening in your system. So here's what we have going on. I initially have a state where I have flow through only one path to one customer right here. Now, I have a control valve that is set to be a pressure reducing valve, where it's controlling the downstream pressure to 45 psia. I also have a CV versus open percent table, and after that I have several valves right here which are going to open up at different times, which will start allowing flow to different customers. Now, if I was to open up any of those valves, really what's happening is each of these valves are coming on in 30-second intervals. So this valve comes on at 30 seconds, 60 seconds, 90 seconds, and 120 seconds. So again, this can skin the cat in multiple ways. Initially, this guy is closed, so the special conditions apply in Fathom XTS in the same way that they do in Impulse. And here's my transient. The transient profile dictates that this valve is going to open within 1 second all the way. So if I look at that graph here and click on Show Graph, we can see that at time 0, it opens up within 1 second. However, we are using a single event transient. This is where single event transients are a little bit more useful for using time absolute, because it saves me from adding on additional data to my table. If I wanted to use a time transient and I did not want this valve to open up for 30 seconds, here's how I would have to do this. I would have to say at 0, the CV is 0. At 30 seconds, the CV is still 0. So in the first 30 seconds, that valve does not open. And then since I know that it's going to open in 1 second, I would do 31 seconds. Bam, it's fully open at that point. So if I wanted to do a time-based transient and I wanted this valve to open 30 seconds after the simulation is started, here's how I would have to do that. However, if you were to do a single event where it's set to time absolute, it makes it a little bit easier for you, because you don't have to define those extra data points up front. Just tell it, hey, wait 30 seconds and then start to open along this profile. So that comes on at 30 seconds. This comes on at 60 seconds. This comes on at 90 seconds, so on and so forth. Now, as I'm allowing more and more flow into the system, the flow demand increases, and my control valve is going to open up further and further and further to allow more flow. So I have a transient set up on the secondary pump and the valve to allow, or actually not allow, it's going to turn on those two objects once the open percentage on the valve exceeds 50% open. So here's my pump. It's a centrifugal pump. I have set it to be off with flow through, and then my transient is going to use a single event transient in this particular case. And the event type is based upon a valve open percentage. So when I choose valve open percentage, it's going to be when that valve is greater than or equal to 50% for J8. That is my control valve right here. So once the control valve reaches 50% open during a transient, bam, this pump is going to come up to speed within 5 seconds. Now my valve has a it's got a similar transient. It's initially closed. That's what closes off the flow. The dotted lines and the X for special condition and the T for transient mean the same thing in Fathom XTS that they do in Impulse. And so here, I'm using the same type of criteria to open up my valve, but I could do something a little bit different if I wanted. Instead of opening up this valve based upon the open percentage of my control valve, I could base it off pump speed if I want. So if I wanted to ensure that my pump is at least, 10% up to speed first, this is where I can do my pump speed greater than or equal to 10% for J5. So what this would mean is, even though this may be greater than 50% open, if I tell this valve not to open until the pump is at 10% speed, that's when this is going to happen. So again, there's several options that are available to you on how you're going to control your transients for when they activate and when they don't. All right, so now I'm running my simulation and we can see what happens. So let's go to the event messages by time. This is usually one of the first best places to start looking at when you are evaluating your transients, either in Fathom XTS or Impulse. So here I can see that my first valve opens at 30 seconds, second opens up at 60, but then it's telling me that my pump and my valve, the secondary ones, those are kicking on at 65 seconds. And then the last two valves open at 90 and 120 seconds, which is exactly what we told them to. So let's take a look at the pump transient tab here. As we can see, the first pump is initially running the entire simulation, but we have a spike here where it's trying to get to a higher flow, and then that's right when the control valve reaches 50%, and the secondary pump comes online to start helping deliver more flow. So you could right click on any of these columns. You can do a quick graph to see how that looks. If I was to expand the other pump, if I can click the object, we can see here that initially it's at 0. So this again just shows that it's being consistent with what we told it to do. Stay closed until the control valve open percentage reaches 50% and then it comes online. We could look at the discharge valve and we could see that it would be the same sort of thing where I have my, let's see, what valve was it? J6. It's initially closed and then we open it up. If we looked at CV, we can see the same thing. But let's take a look at our control valve. Here's our control valve, J8. And I'm going to right click on the open percentage column. So if we look at this here nice and closely, we can see that at 50% open, bam, right at 65 seconds. So this is what's causing the secondary pump and the secondary discharge valve to come online. This is just another example of using an event transient to cause a component to start doing something or stop doing something based upon some criteria. It's worth pointing out that if the criteria that you specify, if this criteria is never met during a transient, then this transient profile will never activate either. So in order for that transient profile to happen, this has to be satisfied. Now, let me give you an idea of what can be used for a dual event cyclic type of transient. So what I'm going to do is I'm going to build onto this a little bit. I'm going to put another reservoir. I'm not going to actually run this second model. I'm just doing this for a conceptual idea. Actually, I missed something. One thing I forgot to show you is that the supply tank right here, this is a finite tank. So it's draining over time. So if I was to take a look at the output window for the reservoir transient, you can see that that tank drains pretty quickly. If I ran this simulation for a little bit longer than 3 minutes, that tank is going to be fully drained. So here's where I was going to show you the example of what a dual event cyclic would be used for. So I'm going to put in a reservoir, a pump, a check valve, and then I'm going to connect them with my pipes. So this particular reservoir junction, this is a small tank. This could be a infinite reservoir, a very, very large body of fluid. So what's going to happen is this liquid level is going to drain over time. What I want to do is tell this pump to be initially off. And what I want it to do is I want it to cycle on and off over time. This is called a dual event cyclic. So if I choose dual event cyclic, you can now see that there are two events that we're dealing with. The first event needs to correspond with the initial state, which is the pump being off with flow through. So here, my pump is initially off. That's going to be a speed of 0% at time 0. I want my pump to come on in 5 seconds at 100% speed. Now, when is this pump going to start to come online? That's going to be the event criteria that I'm basing it off of. And I'm going to base it off of a liquid height. So I'm going to say when the reservoir liquid height gets to be less than or equal to 2 feet in the J1 reservoir right here, this is when I want that pump to kick on. So when that pump kicks on, it's going to start filling up that supply tank again. Now, we don't want that supply tank to overfill. So this is where I'm going to do my second event transient, where I'm going to shut the pump off. So it's going to be operating wherever it is at 100% speed, and I'm going to trip the pump within 5 seconds, and in 5 seconds it'll come back down to 0% speed. And so now I could base it off of the same criteria if I want, but this could be once the liquid level gets to be greater than or equal to 4.5 feet, bam, that's when the second transient profile is going to activate. So as this tank liquid height drains and fills and drains and fills and drains and fills, this pump is going to continue to cycle on and off and on and off over and over and over again. So that's what is a dual event cyclic. It's where you have two transients that are activating, and they will continually cycle with each other over and over and over again. There's another thought experiment example that I can show really quickly. It's how you could use a regular valve junction to simulate a check valve. So in this particular simulation here, I'm doing a pump trip, a pump trip. So when the pump trips, I could potentially have reverse flow. So I'm specifying a check valve that's going to close when the velocity reaches 0. Now, if you're using a check valve junction in Impulse, Impulse version 7 has some new and much, much more sophisticated options for defining the behavior of that check valve junction. So it has its own transient event criteria built in that will change it for you. You don't have to set up any transients yourself. As you can see, no transient tab. Now, let's say that I don't have any information for any of these sophisticated methods for my check valve, and I need to do something a little bit more simple. Well, all I know is the full open CV value of my check valve. I know the velocity at which it closes. I know the pressure at which it reopens, and I might have some sort of idea on how long that might take. So what I'm going to do is, instead of using a check valve junction here, I'm going to use a regular valve junction to simulate a check valve. So I'm going to hover over the valve and hold the control key down, click and drag that valve to be right on top of the check valve. And then when I open that guy up, I'm going to go to my Transient tab, and I'm going to set this as a dual event cyclic. Now, this valve is initially open, so I'm going to keep that special condition set as none. So because this valve is initially open and the fully open CV is 100, that's where my first data point has to start at for my first event. For your first event, the first transient has to match your initial condition. So at time 0, it's 100% or 100 CV. And how long does it take this check valve to close? Let's call it 20 milliseconds. And we're just going to assume that it closes linearly. Now, what causes this check valve to close? Well, typically it's going to be based upon the velocity, probably, of the upstream pipe. So if I set my event type to be based upon velocity, once the velocity gets to be less than or equal to 0 feet per second at the inlet of pipe P3, that's going to cause my valve to close and slam shut. Now, I could potentially have a pressure buildup later in the system, which causes my valve to reopen again. How long would it take that check valve to reopen? Maybe it's 40 milliseconds. So it takes 20 milliseconds to close, 40 milliseconds to reopen. And this time, the criteria that's going to cause it to be open is going to be based upon a pressure difference across the junction. So here I'm going to say pressure difference at junction. Once that pressure difference is greater than or equal to 5 psi, and then this time we pick the junction that it's based upon, which is J3. So when the pressure difference across this valve is greater than or equal to 5 psi, that's when that check valve is going to reopen again. And this is another good example of where you would use a dual event cyclic type of transient to simply allow a component to cycle between two different conditions over and over and over. And that will allow this valve to function just like a check valve in reality. Now, I know that we're running short on time here. I'm not going to go over what you would be able to use a dual event sequential event for. If you would like an idea of where you would use that, go to our video tutorials page, and then you can filter it by impulse and technical, and watch this video here, dual event sequential transients. This is where I made up an example of how you might use this type of transient for modeling something in your system. So watch that video, and it'll give you an example of what a dual event sequential type of event transient would look like. The reason why I'm skipping that for right now is because in the last few minutes, I want to demonstrate a new and awesome capability that came out with XTS for version 10 of Fathom and Impulse version 7, and that's what we call multi-condition event transient modeling. Long story short, it allows you to model and or types of logic. So let me go ahead and open up that model here really quick. All right, so here we have a very simple system, and I'm using this with Fathom XTS because, well, A, I already have a model that I've built for it, but B, it's a little bit more easy to quantifiably understand what's going on. So here with XTS, I have two finite tanks that are initially empty. I have defined my geometries for each of the tanks accordingly. And as you can see here, based upon the cross-sectional areas as well as their elevations, the tanks are different. So you can see how we've got 150 square foot diameter tank here. We have a 150 square foot tank, but it's got a different elevation. So here's my situation. The tanks are initially empty, and this pump is just going to be operating at 100% speed, and we are filling up the tanks. I have two reasons why I would need to close this valve. One reason is I want to close the valve if my desired liquid level in both tanks is achieved, or if the liquid level in one of the tanks gets to be too high. So if I was to open up each of these tanks, my tank heights are 30 feet for each of these. So I definitely don't want to overfill the tanks. So here's my situation. I've got two different scenarios. I have a situation where my desired liquid height is 15 feet in both tanks. That's what I want the fill level to be, is 15 feet. The other scenario is where I want the tank heights to be filled to 20 feet. So let me go and load the 15-foot scenario here. So as you can see, I have a T in front of the J3. That means I have a transient on the valve. So if I go in and I open up the valve here, and I go to the Transient tab, we can see that if you did a single event and you chose, you went all the way up to the top, there's this new one called multi-condition. Well, when you do multi-condition, what you're going to be using is the multi-condition event manager to model your different types of transients. Now, as you can see, there's a very simple transient here that causes the valve to close in 30 seconds. So that's how fast the valve closes. That's the easy part. The question is, why does the valve close? Does the valve close because both of my tanks get to be the desired liquid height, or is one of them about to overfill? That's where I have three of these different multi-condition events. If I was to drill down on each of these, we have shut off the valve if the liquid level is too high. So the criteria that I've specified for that liquid level to be too high, if you read that, it says if the liquid level is greater than or equal to 27 feet, that's where you would shut off the valve. And this is using OR logic. So if either of these two tanks gets to have their liquid levels be greater than or equal to 27 feet, shut off the valve with this criteria. The other reason is shut off the valve because both tanks get to be the correct height. So as you can see in this scenario, the desired liquid height that I want is 15 feet in both tanks. So if both tanks get to become 15 feet full, that's when the valve is going to shut off. And then this event is going to use either of those two multi-condition events. So if you want to see how you set this up, you just do it in the multi-condition event manager. First, you define your simple events. So my 4 events are if discharge tank 1 is too high or tank 2 is too high, or if my desired fill level is met, or my for both of those. So here, my discharge tank too high, 27 feet. So if either of those tanks are over 27 feet, that's going to activate the valves to close. My desired fill level is 15 feet. That's why I want the liquid heights to be when they're filling up. And then after you set up those criterias, you would define your and or logic down below. Now, I'm not going to go through the process of how to set this up. The key thing is to read the help file, and we also have a blog article on our tips and tricks page that illustrates how to do this. So I just want to show the results. So in this scenario, we're going to see why the valve closes, and we want to achieve 15 feet for the liquid height. So let me go ahead and run the model. So I'm running this scenario here, and the first question is, when does this valve close? Well, that's going to be determined on the event messages tab. So 97 minutes. So we turn this on, and we're operating and we're filling up the tanks. At 97 minutes into that simulation period, the valve closes. Now, why does the valve close? Is it because both tanks achieve my desired height, or is one of them about to overfill? That's where using the graph results is a lot more useful. So here I have my liquid height versus time graphs that I've already specified. And so as we can see here, both tanks get to be 15 feet. This tank here, let's see how high that gets. If I turn on my crosshair, this gets to be 25 feet. So not quite 27 feet. So the reason why the valve closes in that case is because I have 15 feet here, and my second tank also achieved 15 feet. So because my second tank achieved 15 feet, that's what caused the valve to close. And you can see it close accordingly at 97 minutes. So 97 minutes, that's exactly the time where my second tank gets to be at a liquid height of 15 feet, right at 97 minutes there. That's when that valve closes. Now, my other scenario is where I have an operating condition where instead of needing only 15 feet for my liquid height, I need a little bit more liquid in each of those tanks. I need 20 feet. So in my multi-condition event manager, I just changed my desired fill level to 20 feet here, and then 20 feet here. So I need more liquid in each of those tanks, and we're going to see when that valve closes. Thankfully, the simulation doesn't take too long to run here. All right. So this time, the valve closes at 107 minutes. So the thing is, we have not changed anything about the system. We've not changed diameters or operating conditions or anything. The only thing that we've done is changed our criteria where we need 20 feet of liquid level in each of these tanks instead of 15. And our valve closed at a much different time. So let's go back to our graph results window and let's plot that liquid height versus time again. So here, if I right click on my y-axis and let's make this be a finer time resolution here, let's look for 107 minutes. So I'll make this every 5 minutes. Okay, so 107 minutes would be right around here. So if I turn on my crosshair, so here's 107 minutes. This tank gets to be 27 feet. So this first tank is just about to overfill. If I look at my second tank, look at this. It's still not up to the 20-foot liquid level mark yet. So because the second tank is still filling and it's not at the desired level, but because one of the tanks is about to overfill, that's what shuts off the valve. And this is an example of how you can use the multi-condition event manager to be able to use either and or types of logic to do some more sophisticated transient modeling. And the multi-condition event manager applies to both AFT Fathom with the XTS module, as well as AFT Impulse. And let me show you where you can find that blog article really quick on using multi-condition events. So if you do if you go to the tips and tricks page on our Learning Center and then do a search for multi-condition, I know that there's one in there. Well, let's try it this way. Maybe that's not what the title is called. So if you scroll down, I believe it's on the second or third page. Here it is. So it's called And Not Or, Starting Transient Events with Complex Logic. This is an excellent blog article that talks more about multi-condition events and how to set them up. And then our documentation of the help file also explains it in more detail. Okay, well, that takes care of it for today's webinar. Thank you all very much for your time and listening in. I hope that you enjoyed the material. If you have any questions, please don't hesitate to contact us and give us a call. And have a wonderful rest of your holiday season and an amazing new year. And we will see you all in our webinar next year. Take care, everyone. Have a great rest of your week.